very broadly complexity and quantum chaos in Krylov subspace. This talk is based on some papers that appeared, as I said, recently, and an upcoming paper. And let me provide a very broad motivation for why I'm interested in this. Some people might want more industrial realizations of what I'm doing, but let me keep it very big picture at the moment. So there has been a renewed interest in studying state and operator dynamics in Krylov space. This has been a very fruitful pursuit, some of you are aware of, and this has led to new probes of state and operator complexity and to new avenues of studying quantum chaos in many body systems and holography. So to name a few things that people have been interested in recently, there has been an uncovering of interesting relations to out-of-time order correlators and new conjectured universal chaos bounds. This goes by the name of universal operator growth hypothesis. And that was present in the original paper where people were interested in studying this operator growth. There have been interesting connections with holographic complexity in the context of double-scaled SYK and JT gravity. And more recently, also in the context of momentum complexity growth rate correspondence, new tools to study long time or late time quantum chaos and encoding of random matrix theory behavior, for example, spectral rigidity, and also perhaps something that is also interesting to a part of the group is new connections between quantum chaos and quantum computation. So these are some of the things why people are interested in this. And the two key characters, the main ingredients of this story that I will tell you about today are Krylov and spread complexity. They are essentially the same thing, but for historical reasons, they have a different name, but they are talking about essentially the same idea. And Krylov, which I color-coded in orange, typically refers to operators, operator complexity, and purple I will refer to as state complexity.
Can we ask questions along the way, or?
Sure, if you want. Yeah, it's up to you.
I mean, quantum chaos can mean many things. For example, it can mean certain behavior of out-of-time order correlation functions. So then,
sure.
That is a kind of tautology, because quantum chaotic systems are then, by definition, of the type that they have certain scalings of out-of-time order correlation functions. Is that what you're doing, or do you have other notions of quantum chaos in mind?
Well, the working definition that we use is based on spectral statistics, essentially. That's the working.
Gaussian neutron ensemble like.
Yeah, things like that.
Good.
That's what we refer to.
Wonderful.
But this question about OTOCs will also come up when I discuss operators. So in this talk, I will focus on some of the properties of these two quantities in the context of quantum systems with finite and infinite dimensional Hilbert spaces. I will tell you some things about Krylov complexity for QFTs in flat space, in quantum billiards, and I will tell you about state complexity in quantum spin chains and random matrix theory. This does not mean that these quantities can only be studied in this context. These quantities have been studied in a variety of settings. It would be interesting to see if these things have realizations in tensor networks or more concretely in quantum circuits, but this is what I have done and this is what I will tell you about today, but I'm happy to hear any questions that you may have. And the starting idea is very simple. We want to study the time evolution of states or operators. So if you take a dynamical quantum system with a time-independent Hamiltonian, you can formally write the power series expansion of the time-evolved state as applications of the Hamiltonian. I don't know if this works. I think the hand is slowly moving, but I don't know why it's moving in such a... I don't know why it's doing that, but I'm trying to point to the left side of the screen. So just imagine my hand pointing at the left side of the screen. And formally, you have a basis for what is called the Krylov subspace of the full Hilbert space. And this space is spanned by these applications of the Hamiltonian on the initial state. Similarly, for an operator who is evolving under Heisenberg time evolution, you can also write formally a power series where now the operator that acts on it is what people call sometimes a super operator, which is called the Liouvillean, and it acts by commutating the operator with the Hamiltonian n times. And this also creates a basis of operators in Krylov subspace. Now, these states, psi-n and on, span this subspace, but they are in general not orthogonal or even normalized. So the very simple idea, and this is the basis for what people call the recursion method, and it's something that people in condensed matter have done for a long time. People use the so-called Lanczos algorithm to create or to find an orthogonal basis from these states in Krylov space. And the logic is very simple. You start on the left side. I'm also pointing, but the hand does what it does here. So the idea is very simple. You start from some state that you're interested in, and you have your Hamiltonian, or you start from some initial operator, and you have your Liouvillean and a choice of inner product that will essentially be equivalent to choosing some state in which you're taking expectation values of the operator. You have this unnormalized basis in Krylov space, and then you apply essentially Gram-Schmidt procedure, and then you obtain an orthogonal and normalized basis in Krylov space. And why do we want to do that? We want to do that because essentially this transforms your Hamiltonian or Liouvillean to a three-diagonal form or Hessenberg form. And the coefficients that appear in this three-diagonal form of the Hamiltonian or Liouvillean contain not only information about your state, but also about the dynamics of your system. Mm-hmm. So this is, you can think of it in contrast with the usual eigenbasis, where you just have information about the Hamiltonian, about the full dynamics, but it's only information about the Hamiltonian. This three-diagonal form has information about both your initial state or operator and your dynamics. And these elements are called Lanczos coefficients. And so what is interesting is that if you now write your time-evolved state or your time-evolved operator in this Krylov basis, the coefficients in this basis have the interpretation of probability amplitudes. And the Krylov complexity of operators and spread complexity of states are formally defined by taking this weighted average of these probability amplitudes. This is on the, formally it's the same thing. Any questions so far? If I'm going too fast, you can also tell me.
No, I don't have a question. It's like more like a meditation. That I mean, okay. I'm aware of the spread complexity and Krylov complexity. Do you have like any operational interpretation in mind? Like, of course, they're both in a way related to obstructions against classical simulation, right? Because it's a non-sparsity somehow.
Okay.
Will you say more about this, or is that, do you take quantities for granted and then you say something about them?
I will comment in the next couple of slides. I comment a bit more about these quantities individually and what interpretation I can give to them. Mm-hmm. So if it's still not satisfactory after two slides, you can ask me again. So yes.
Yeah, I can also, general question. So yeah, I understand that once you write a state or an operator in this Krylov basis, the spreading of the operator there tells you something about this complexity grow, blah, blah.
Yeah.
Good. But then you define, not everyone, no, Krylov complexity as that quantity. Then somehow this amplitudes square weighted by this n. So
yes.
How you give more weight to the larger guys, no?
Yeah.
What is can you say something about the intuition or why that makes sense? Or?
So the intuition is the following. So essentially, you're translating this complicated time evolution problem into a one-dimensional problem. You are constructing essentially a one-dimensional chain of states. You have your initial state, your psi1, psi2, psi3, et cetera, et cetera, et cetera. And then these probability amplitudes are somehow probability amplitudes on each individual side of this Krylov chain. Mm. And what this Krylov complexity or spread complexity are measuring is the average position of your state in the chain as time evolves. Okay. So this is supposed to provide a measure of how much or how fast this state or operator is spreading in this Krylov chain. So that's interpretation.
Position n with probability phi of n.
Exactly, yeah. Yeah, so this is, yeah, exactly. So this is essentially the idea, and this is like something that I will also come back to in the next few slides. Mm. But there was another question.
Yeah, a very related question. Right, so this is the average position.
Yeah.
But what about other average? And you can compute it more easily.
Like variance and other things, or?
Yes, but like if you go further down the chain, stuff gets more complicated.
Yes,
But
that's
not
the
too
idea. In what sense, or
like,
what can
like
come?
the computational cost of simulating this on a classical computer or quantum computer should scale with how deep you are in the chain. And of course, if you don't have a concrete model, then it doesn't make sense to specify something concrete. So n is fine, but
yeah, in principle, like you could. I will also mention this a bit more, like in a couple of more slides, in the context of states. But you could replace this this quantity n by some monotonically increasing function. And there are some statements which you can make up with some generality about them.
Yeah.
But I will come back to this in the next few slides. So ask me again if I don't answer. Okay, so let me provide some background for each individual quantity. So this Krylov complexity is supposed to provide a measure of how operators grow in Krylov space. And in the original paper where it was introduced, it was an example of a more general class of growth measures that the authors called quelconque complexities, or whatever complexities they call them, or Q complexities. And these are a class of operator growth measures arising from positive semi-definite operators in Krylov space. You can think of operator size being another example of Q complexity. You can think of certain OTOCs as being another example of Q complexity. And you can define operators in Krylov space. One example is this spreading superoperator. And if you take the expectation value of this superoperator in the time-evolved state, GNS state, corresponding to the operator, then you recover the Krylov complexity. So what essentially you're doing, the question that you're asking is, you start from some initial operator that has a time zero just support on itself, but as time goes on, you acquire more contributions from different elements in the Krylov basis, and this Krylov complexity is going to measure how much this operator is spreading in Krylov space as time goes on. So starting from a simple operator, say you can start from a local operator, and then this operator will become non-local with commutation with the Hamiltonian, and this is providing for you a measure of how complex this operator becomes as time goes on. And this is what I mentioned before. Like, you can think that you're translating the problem of time evolution into a one-dimensional problem where these coefficients, ANs and BNs, have the interpretation of hopping probabilities between different sites in the chain. And this is a recursion relation that is just a restatement of the Heisenberg equation. And you can obtain all the probability amplitudes by solving this equation starting from this autocorrelation function. So if you know this autocorrelation function, this two-point function of the operator, then you can, in principle, construct all the probability amplitudes.
So can you again put in the auto? I missed it. Where's the auto?
Here, there is no auto. No, I just mentioned that this Krylov complexity is an example of one operator growth measure.
Yeah.
There are other operator growth measures, for example, operator size or OTOCs. And these are examples of these Q complexities that appear.
The relationship between them is known, understood? Or?
So, okay, you're jumping a bit ahead, but the idea is that this Krylov complexity, the growth rate of this Krylov complexity bounds all growth, all these other growth measures. So this will come back in a few slides.
Okay. Maybe a related question to that. I see this is measuring operator growth in this Krylov space. But is there any relation to the operator growth in real space?
In principle, you might think that this operator has also some support on, is it like a, I don't know, local operator, probably. So this will tell you about the spreading of the operator only in Krylov space. So it does not tell you necessarily how it grows on real space, for example. Yeah.
If there's like algebraic constraints, like, I don't know, integrable models, 3 bosons, 3 fermions, then you get a very small Krylov complexity. That must be visible somehow, no?
I will, yeah, I will tell you a bit more in a few slides. I think you're still like a bit ahead of.
Oh, I'm sorry.
Yeah,
sorry.
That's okay. Yeah, but there are like people have studied this in like many body systems and QFTs and things like that.
Also, this picture is very thought-provoking because it reminds you of diffusive and ballistic transport.
Sure.
And but here we don't know. Could it be that we have something where the Krylov complexity grows faster than linear in T?
The Krylov complexity essentially will grow exponentially if you have a in T. Yeah.
Yeah.
Exactly.
Nice. Sorry.
No, it's okay. No, it's good. Like you're getting ahead. It's great. Makes my job easier. So what about state complexity or spread complexity? So you can think that analogously, spread complexity will tell you how much a state spreads in its corresponding Krylov space. And you can also see this spread complexity as arising by the expectation value of the time-evolved state, the spreading operator in the time-evolved state. Now, also something that might be interesting is that in what sense is this a measure of complexity? And this is something I guess you would find interesting. In the paper where it was introduced, it was argued that if you consider a cost function that looks like this, essentially the BNs appearing here they form some complete orthonormal basis in Hilbert space. And essentially this is measuring how much this time-evolved state is spreading in this orthonormal basis. And the argument that the authors gave in their paper was that if you think about this as a cost function where you want to minimize over choices of basis, then the basis which gives you the minimum is the Krylov basis. So for this kind of cost function where you minimize over choices of basis, the basis that minimizes this cost function is the Krylov basis. Yes.
Yeah. So okay. So this bases are orthonormal, no? This kind of basis. You define it recursively, but then you orthonormalize.
Yeah, the Krylov basis is by construction orthonormal.
These coefficients sum up 1, and right, the absolute value phi and squared because it's an orthonormal basis.
Here, yeah.
Why not take in the entropy of that thing? That's
of course
one that's an entropy that also tell me spreading.
You can also people call this one the K entropy. It's essentially the Shannon entropy of these probability distributions. That is also something that people have.
Okay, so it's really true that anything that more or less tell me how spread these numbers are, would do, no?
In principle, yes. So people are also interested because these are essentially classical probability distributions, and you can do many things with them.
Yeah.
So you can compute the Shannon entropy, for example, and there's like some interesting relation between this Shannon entropy and this spread complexity by some exponential, for example. So this is something that people have studied before. So again, this is the very short version of why this is a measure of complexity in Krylov space. Okay, good. Now, let me tell you why people got interested in Krylov complexity in the first place. And this has to do with semi-classical signatures of chaos. Of course, like Jens said, what do you mean by chaos? Okay, I'm gonna tell you one little story. So in the original paper where Krylov complexity was introduced, the paper is called Universal Operator Growth Hypothesis. The author stated that in the thermodynamic limit, these Lanczos coefficients of generic non-integrable quantum many-body systems with local interactions should grow as fast as possible, which in this context, and with the constraints of locality, means that the coefficients should grow linearly, asymptotically, for large n. So on the left side of the slide, I'm showing a picture taken from their paper, and essentially I'm showing the BNs for different systems, and the growth rate is a reflection of the integrable or non-integrable properties. So this blue line corresponds to the SYK, probably Q equals 4. And then for other systems like integrable systems like the XXX chain, you have a sublinear growth, typically square root of n or to n to some power delta with delta smaller than 1. And for free theories like the Ising, you have essentially an order 1 number of these coefficients. So you can do, in special cases, you can do analytic computations. And for example, for DSYK, you can find in the large n limit, this is an example of obviously what they did was much more than this, at infinite temperature and for a specific choice of initial operator, this is how these BNs look like. And asymptotically for large n, this grows linearly. Moreover, I forgot I had this. Moreover, whenever these coefficients have a smooth linear behavior, the Krylov complexity is expected to grow exponentially, where the growth rate of the Krylov complexity is given precisely by twice the growth rate of the coefficients. And this growth rate should also bound the growth rates of other notions of operator growth. such as OTOCs. So if you think about OTOCs, like this one here at the bottom, then what the authors showed in their paper was that at infinite temperature and assuming a smooth behavior of the coefficients, the growth rate of OTOCs was bounded from above by this lambda k. And they conjectured that at finite temperature, the growth rate of this Krylov complexity would provide a tighter bound than the Maldacena-Schenker Stanford bound. So this is a conjecture. Yeah.
Maybe this is too detailed of a question, but since you mentioned that what is chaotic for you is basically level space and statistics.
Yeah.
At least in spin chains, there's a bit of a subtlety, which is that if you want to get RMT, like Wigner-Surmise level spacing statistics, you always need to look within a super selection sector.
Of course, yes.
Is that also true here?
That's also true here.
So these language coefficients, this is only true within a super selection
Yes,
sector.
you need to look at them within each super selection sector.
Okay, good.
So your initial state has to respect this.
Yeah.
Yeah.
Yeah, in this case, it's a statement about the operator, for example. Yeah.
So operators within a super selection sector. Yeah. Got it.
So that's the statement. Okay.
So what is Q?
Q in this case means that SYK, you can think of how many fermions are interacting, and Q tells you like how many, like what's the, how many interacting fermions you have. The order of the interaction in the fermions, no?
Like K and K mode.
Yeah.
Okay.
Good.
Related to the superselection sector, for the linear length of so just for the linear growth of length of the coefficient, should we only consider if I don't consider superselection setup, can we also see the linear growth?
That's a good question. I think no.
I don't think you will, because the point is that within different states, eigenstates in different super selection sectors don't have any correlation.
But here, for the operator growth, I don't think the specials. I don't think the level statistic is so important. Yeah.
Okay, for states, I know that it's important. For operators, I would argue
for this slide.
For this slide.
Yeah.
So in the same sense that maybe for OTOCs, you don't necessarily have to look at this kind of special operators.
I think so. For example, in SYK, I can consider the initial operator like a single Marana plus a double Marana, a boson, a fermion plus a boson is operator, yeah. Then operators, they are not belonging to, they don't belong to the same super center. Yeah.
Okay, then let me refine my answer that I gave you just a few seconds ago. I would say that for states, it is important. At least that's what I know, what I have done. For operators, I was under the impression that you also needed to do it, but probably it's not necessary.
Okay. Cool.
Okay. Wait, what happened? Okay. Now, in one of the papers, I don't know how much time I have. I'm going, I think, very slowly. But I guess it's up to you.
The Christmas party starts at 6, I think.
So Jens will leave.
The Christmas party starts at 6.
That's right.
We have
Okay.
So no later than 6.
No later than 6.
6 and a half account. And the soft hour one for me is 4, because then I teach.
Then you teach?
But
Okay.
that's my problem. You can just go ahead.
Okay, well, so obviously, like one of the first questions that we had when we came across this this Krylov complexity was, well, these statements were formulated for many body systems. What happens if you take a QFT? So if you take a free QFT, you expect it to be integrable. So we would expect that you would recover the properties of a free theory according to these previous statements. So what we considered was a free and real massive scalar in these space-time dimensions, where the Lagrangian is given by that. Please excuse me if you're not so familiar with the language, but I hope it's not too terrible. So now what we want to study is we want to study the Krylov complexity of the field operator, this field phi. And this is an infinite dimensional Hilbert space and continuous theory. So we want to study also finite temperature effects. So the starting point for our computations was the so-called Whiteman two-point function, which is given by this expression here for people who are online, I guess. And one reason why we want to focus on that particular two-point function is because it comes from taking what is called the Whiteman inner product of operators. You can write how this two-point function comes from choosing the Whiteman. And this two-point function is related to the spectral density and power spectrum in the following way. So the Fourier transform of this two-point function is the power spectrum. And at finite temperature, this is related to the spectral density in this way, where the only, oh no. Now I understand, sorry, but why is it so slow? Okay, this is the only place where the temperature comes in, and then the spectral density, this is too slow, the one in red.
How is it supposed to know that the screen is there, right? The receiver is here. So maybe you point there. Nothing happens.
Okay, well, the input from the free theory is that the spectral density is given by this part here on the right. Now, in this case, we don't explicitly construct the Krylov basis, but we can find the Lanczos coefficients from the moments. Essentially, there is an equivalence in how the dynamics is contained in the coefficients, the moments, the two-point function, and the power spectrum. So the moments which you compute by either of these two expressions can give you the Lanczos coefficients in a nonlinear way. In this case, these AENs, which were part of the diagonal, are zero because this field phi is Hermitian, and for that particular choice of inner product. So what happens in this case? You can explicitly find the power spectrum for any d greater than 3, and that's the expression. And this n is some normalization constant. And what you see is that the mass of the scalar field acts as an IR scale. And what this does, it induces what people call staggering or dimerization of the Lanczos coefficients. However, and this was a bit surprising at the beginning, was that asymptotically, they still grow linearly with a fixed growth rate. So for small n, this is the behavior. And for large n, the asymptotic behavior, you see that they still grow linearly, where the separation is given precisely by a scale proportional to the mass. And then you will complain, you will say, Hugo, but you told us that if your system is chaotic, then this will grow linearly. Then this doesn't work at all. And then I will tell you, well, there is a reason why in continuous theories it's a bit more subtle. And the reason is the following. The decay of the power spectrum is related to the pole structure of the two-point function, and it's also related to the growth rate of the Lanczos coefficient. So essentially, if you have a two-point function, which is analytic on a complex strip that looks like this, which has two poles in imaginary time, the position of these poles is directly related to the exponential decay of the power spectrum in that way. And because they are related essentially by a Fourier transform. And then the moments that you get by integrating omega to the 2n with respect to the power spectrum, and then getting the coefficients from these moments will also inherit this property from the two-point function. So this is a statement about the pole structure of the two-point function in QFTs. And in fact, if we compute explicitly the Krylov complexity, then we see that it still grows exponentially. However, the growth rate is now not exactly 2 pi, but it suffers from some decrease in how fast it grows due to the mass. And in fact, if you take the massless limit, then you recover what people have known for CFTs. So this is
these results are always, I mean, there's the left-hand side is like numerics and fitting, and the right-hand side is curves. And that's done via CFTs, the right-hand side. Or what's
this was on
the red box.
This was a fitting that we did for the numerical data.
Fitting.
This is a fitting that we did for the numerical data.
Okay.
Yeah. The point is that you still see some exponential behavior, and this is
okay.
This
I see.
is clear.
Okay, then I missed this.
No, sure. Yeah. So in this case, like this behavior is a consequence of the pole structure and does not imply chaotic behavior. This is an important thing to keep in mind. So what we thought was like, okay, well, how can we recover the properties of the free theory? We need somehow change the UV. And one way to do it is to put a UV cutoff in the power spectrum. And then, for example, this is in 5 dimensions and for some choice of, this is in 5 dimensions. And what you see is that this cutoff capital lambda, it induces a scale after which you recover the behavior that you would expect for a free theory. So in the case of the coefficients on the left side, after this scale inserted by lambda, then these coefficients now saturate, which is the behavior that you expect for a free theory. Correspondingly, at the similar timescales for Krylov complexity, you see a transition from an early time exponential growth to a linear growth. And this is consistent with some lattice computations that authors did also in similar setups. You can also try to change this behavior by adding perturbative interactions. I know that this is probably not the most interesting thing for this audience, but I still want to mention it. You can try to modify the Lagrangian and consider interactions, but the punchline is that these perturbative interactions do not change this behavior. Like in one case, the effect amounts only to introducing something called a thermal mass in the field, but this does not change the slope. On the other case, it also induces a staggering, but which decreases as n increases. So this was not like, this is not the correct way to look at it. One thing that we thought about, and this is just as a comment, the correct thing to do would be to consider what people call an irrelevant deformation, which is a deformation of the theory which changes the behavior in the UV. But we can talk about it later if you're interested.
Maybe a question related to that.
Sure.
Does the complexity change along an RG trajectory?
Okay, what I can tell you, and I don't know, probably you also know about this, but
does the complexity change along an RG trajectory?
Like I'm familiar with some papers that studied this in the SYK, and they were somehow saying that this lambda k of complexity is like a parameter that.
Yeah,
like what if your interacting theory becomes free in the UV, in the IR?
People, in SYK, people do some numerical simulation.
Yeah.
They consider whatever deformation for the SYK4. I don't know. They consider SYK2 plus SYK4. And then people expect that you will see the SYK2 behavior in the IR. So,
SYK2 is integrable.
Yeah.
So you're saying that in the IR, people expect the complexity to, well, the aftermath of going from chaotic to integrable should be observable in the complexity, is what you're saying.
For example, I think if you consider very late time or very low temperature, then you will see the decay of the length of coefficient.
I see. Got it.
Yeah, but we can certainly talk more about this. So now coming back to the question that Jens also asked at the beginning, like, what do we?
Sorry,
Sure.
I see a question. So,
Sure.
is the plateau of the length of coefficient related to the scrambling in this case?
In this particular example, no, this was also an artificial thing. We just put a UV cutoff because we wanted to see more clearly what happened with the.
Okay, so
you
say
the staggering.
The cutoff is not related to the.
No,
okay.
no.
When you say scrambling, do you mean in the real space?
Yeah,
Okay,
I mean this way. Yeah, of course.
Okay, good.
Yeah.
Okay, now, so I also had a question before the talk, like, what do we mean by quantum chaos? And I would say that our working definition of quantum chaos is derived from the study of quantum systems that have classically chaotic analogs. And one example is quantum billiard. So if you take, for example, the billiard that I'm showing there, the idea is very simple. You take two particles that have very similar initial conditions, similar position, and similar initial velocity. But in a chaotic system, after some time, their trajectories will deviate exponentially in time. And these ideas were brought to the quantum realm through this Bohigas-Giannoni-Schmidt conjecture and the corresponding Berry-Tabor conjecture. And they state that if you have a quantum system which has a classically chaotic analog, then the spectral statistics of that system will adhere to those of random matrix theories, and in particular, the Gaussian orthogonal ensemble for time reversal invariant systems. And if you have a system with a quantum system with a classically integrable analog, then the energy level spacing statistics will follow the Poisson distribution. And this is exemplified by this picture here. I don't know how familiar you are with these ideas, but essentially, this plot here is supposed to tell you the probability of finding two states with a fixed difference in the nearest neighbor energy difference, for example. X is the energy difference between two neighboring energy eigenstates, and Px is the probability of finding states with that fixed energy difference. This curve here, which is called the Wigner-Dyson distribution or the Wigner-Surmise, is supposed to represent the fact that chaotic systems have a feature called energy level repulsion. Energy eigenlevels cannot be very close to each other. So the probability of finding two states with the same energy is essentially zero. That's the idea. Correspondingly, if you have integrable systems, then there is no restriction between how close two energy eigenlevels can be. And this is exemplified by this Poisson distribution, which tells you that there is a very high probability of finding states even with degenerate energy. The other property of chaotic systems is spectral rigidity, which is a statement about correlations between energy states that are not necessarily adjacent to each other. And that's the statement. So what we wanted to do in one of the other projects, among other things, was to essentially try to study Krylov in this quantum billiard setting. And one question, very simple question that we had was, is the growth rate of the Lanczos coefficients bounded at finite temperature? So numerically, this is a very simple problem that you can pose. So you want to solve the Schrödinger equation for a free particle where you are just changing the boundary conditions on the billiard. If you take a circular billiard corresponding to an integrable system, you can find a solution. And then you want to deform the shape of the billiard in such a way that you are changing these integrable properties of the system. And essentially, it will become chaotic. And then you can fix, for example, this A and R are essentially these quantities that appear here on this picture. And A controls how much you are deforming the integrability of the billiard. And this ratio tells you how much you transition from integrable, which is A over R to 0, to chaotic, which is A over R equals 1. Now, this is a bit like a bit tricky, but essentially, this is an infinite dimensional Hilbert space, but you want to put a cutoff to do some computations. And what you see is on the left side, these are the results for the Lanczos coefficients in the chaotic case as a function of the temperature. And you see that at low temperatures, they roughly follow a linear growth, which is more difficult to see as you increase the temperature. And we want to study in this case the growth. Something that I forgot to say is that we want to focus on the growth of the position operator. And now, in the case of the integrable billiard, we still find some growth of these coefficients, but we have a much larger variance in the behavior of these coefficients. So it's very difficult to say whether this growth is linear or not. But what we can say, and this is something that also people in the community saw, was that larger variance in the coefficients meant integrability, which maybe seems a bit counterintuitive, but this is something that they found. But if you're a bit more careful about the chaotic case, what you can see is that the growth rate of these coefficients actually satisfies this bound. And at high temperatures, it's a bit more difficult to actually. Okay, it's making it great. At high temperatures, it's a bit more difficult to actually make sense whether it's like linear or not. But the point is that at low temperatures, you can roughly say that this bound is satisfied.
But then I'm not following, because I mean that saturates at n.
I'm sorry.
Like we mean, like it's the. Are you looking for the low end limit, or like what's the
sorry.
linear behavior?
No, sorry, this is not. Yeah, it shouldn't be n. It should be t. This was my mistake. Yeah, sorry, it should be t, not n. Sorry. Yeah. Sorry. You're absolutely right. There were some other interesting papers also by one member in the audience. Essentially, they found equation of motion for Krylov complexity, and we also looked at this very interesting equation. But however, I think that the point of this small toy model was that in this like one particle system, it's a bit difficult to actually make some sharp statements about chaos. I think that's more or less what we got from this project. So now let me change gears and move to state complexity and long-time quantum chaos. I'm a bit below slow on time, but hopefully it's not too bad for Jens either. So as I mentioned at the beginning, spread complexity can be defined for any state And because of different reasons, you might want to study different states. In high energy, typically one state that we are interested in is called the thermophile double state. This is because we would like to, for example, compare the spread complexity of this thermophile double state with other spectral quantities, like the spectral form factor. So it's natural to think about the thermophile double state. For those who are not very familiar, this TFD state is essentially the canonical purification of the thermal density matrix. And this zeta here that appears is the thermal partition function, which you can write for a system with discrete energy levels in that particular way. Now, what is interesting about choosing this as our initial state is that the first probability amplitude of the state is directly related to the spectral form factor. So this 2-point function, or this return amplitude of the time evolved TFD state is essentially the square root of the spectral form factor, where the spectral form factor is given on this right-hand side. Now, the spread complexity of this TFD state will only depend on the spectrum of the theory and on the temperature. Two quick facts is that regardless of whether your system is chaotic or integrable, there will be a universal quadratic early time behavior. And at the same time, at infinite temperature, the saturation value of the complexity of the thermophile double state will not depend on these features and will only depend on the dimension of the Hilbert space. At finite temperature, there are some corrections. Okay, and in this case, what we wanted to study is spin chains that have a well-studied transition from integrability to chaos, because we wanted to see, is this a good quantity that can probe chaos, and in what way can it probe chaos in the sense of spectral statistics? And the two Hamiltonians that we looked at were the next to nearest deformation of the XXZ chain and the mixed field Ising. And for these particular values of the couplings in the Hamiltonian, they have chaotic and integrable properties. Now, there are things that you want to take into account, like it was mentioned before. If you have symmetries in your system, you need to resolve them. You need to make sure that you block diagonalize your Hamiltonian with respect to these quantities. If you have a conserved charge, then your Hamiltonian will have a block structure where each block corresponds to a different value of the conserved quantity. And you also want to unfold the spectrum, which is like essentially you are accounting for local densities of states. Okay, so the results are the following. The top row is just about the TFD state at infinite temperature for the two models. So what you can see is that when the system is when both systems or in either of these systems is in a chaotic phase, the spread complexity will have a peak before it saturates. And at the same time, in the integrable case, the saturation value will be very close to the one that you get for the chaotic case. That's one thing that you can see. And now the bottom row is for the thermophile double state in the mixed field Ising. Typically, these Lanczos coefficients have the following behavior. You have a very fast growth and then a descent. But you can see that there's not much qualitative difference between their behavior. I'm not showing it here, but the variance in the integrable case is higher than for the chaotic case. And then the effect of the temperature is essentially changing the saturation value of the complexity. So
maybe a side comment. So
Sure.
for the XXZ chain, you also have then a conjectured NBL phase. Conjectured NBL phase. Enabling localization.
Yeah. We didn't take it into account.
So you don't know how the complexity would behave in that case?
No,
because I would guess it looks more integrable, but I'm not sure.
Yeah,
I'm sure, because then you have effective quantum motion.
Exactly.
Like, you have like a complete
Sure.
set of commuting observables, and that's
Exactly.
like.
Can one study this stuff in the animators?
Recording
yeah, of
stopped.
course.
And like all the chaotic level spacing skills.
No, the Krylov complex.
Oh, yeah. Because
You
it's
can.
just like an RNT matrix and then.
I will tell you a bit more about it later. But sorry.
I mean, analytical.
Analytic results can get you so far, I think.
On a computer, you can have.
I closed the thing. This is crazy. If I close the screen with Zoom, it stops recording. Oh,
It still says. So you don't What should I do?
This I hate. It's like one step, and then why can't it just not record when it's my computer's not on?
Do you want to start a second recording and merge them, or?
Actually, Frederick is also recording this whole thing.
Okay, then okay, that's good. Then Frederick does it.
Thanks, Frederick.
Yeah.
Stupid beginner's question. These
Yes, okay.
ends
Sure.
are the Krylov coefficients,
Lanczos coefficients.
Lanczos coefficients, and they can be positive, negative, complex.
Typically, they are positive for a Hermitian time evolution.
Okay, which is why all of this is positive. And they should sum up, their square should sum up to 1.
No, those are the probability amplitudes.
The BS is how interactive the Hamiltonian ones to get to the stuff.
Yeah, maybe it's a bit.
I was talking about the A's, but these are the B's. In your try.
In the diagonal, you have the A's, yes.
These are
The A's typically do not carry much dynamical information. They just like oscillate around 0, and they can also be negative, as far as I know.
I see. I was surprised why they don't sum up to 1, but okay.
No. These don't have to sum up to 1.
They carry the dimension of energy. So
Yeah, exactly.
they carry their dimension for energy. So they're not similar.
Yeah. I thought it was the decomposition of the state and the probability.
No, it's okay.
It's okay. These are the things I think.
In what I said before, for example, like the growth rate has dimensions of energy, for example.
Yeah.
Maybe another comment from like RMT related, like normally, like if you have spin chain and you want to look at the level spacing statistics, and you go into the super selection sector, you need to chop off part of the spectrum.
Yeah.
Because the edges of the spectrum does
Sure.
something funny. Do you do something similar in your?
I think in these examples, we did not chop anything off.
Yeah.
So
But just consider it within a super selection sector.
yeah, I mean, of course, the point is that if you want your statistics to get better, you can do several things. One thing would be just to take a larger matrix, and then you don't really have to take care about the edges.
Yeah.
But if you're constrained by the dimension, then you might want to chop some part of the edges. That is true.
Yeah.
But here we didn't chop anything.
Okay.
Yeah, that's also true.
So in previous slide you mentioned unfolding. So to calculate Taylor complexity, you use the unfolding spectrum or the spectrum without unfolding.
Actually, here we do not. So for the spectral statistics, it's important to unfold the spectrum. But here it's not necessary to unfold the spectrum. Yeah, it's not necessary to do it. But that is true.
But like, okay, in the behavior,
Sure.
do you? I guess the universal behavior is the same regardless of which Gaussian ensemble you're in. So like the
Roughly.
symmetry doesn't really affect the universal behavior in any way.
No, but I will say something else related to this, in the sense that one question that we had was that, is this structure of having a peak only present for the thermofield double state? Because we tried different states and for these kind of spin models, and we couldn't really see the peak very clearly. So one question was, is this statement also dependent on your choice of initial state? And it turns out that this peak is more or less visible depending on which ensemble you're looking at.
I see. So maybe a related comment to this. In the condensed matter literature, there's a wider classification of Gaussian matrices. So normally in the chaos community, this is the Wigner-Dyson classes.
Yeah.
Which is GU, GOE, GSC.
Yeah.
But in the condensed matter literature, there's a wider ensemble of classes called the Ottmans and Bauer classes. And it's basically just, you take the Gaussian ensemble, but then you're turning on more symmetries and then you're generating more classes. Like you don't only have particle hole and time reversal, you have particle hole and time reversal, things like that. Maybe it might be the case that as you turn on more symmetries, these peaks become more visible.
Yeah, that's a good question. I actually have no idea. I don't know if you have any comment about it.
If you plot the GOE, GSC, and UE inside of this aerosol, you see the height of the peak looks slightly different. They depend on the symmetry.
They depend on the symmetry.
The Dyson index, but not the alpha. The hard gap
only the beta.
And nearly only the beta. Because alpha basically control the edge. Near the origin. So if you have a very huge metric, then you nearly can't see any dependence on alpha.
Gotcha.
I will have something to say about RMTs at the end, but yeah, that's true.
Sorry, I think I got a bit lost.
Sure.
What are we plotting here? Because it seems then that the behavior is the same for chaotic or integrable, or what is the message of this?
Indeed, like it seems like it's very similar. You have a growth and then a saturation. But the point is that the only feature that distinguishes these two cases is the peak before saturation from the chaotic case. So your assessment is correct, I would say.
Okay, so, and your point or what or the point of the
Okay.
story is that you can distinguish because of this peak, no?
Yeah. So that's okay. So yeah, exactly. So the point is that by seeing this, you're like, okay, the peak might be the reason why we look at chaos. So how can we understand this? And typically, when people think about chaos, at least in our community, people talk about this spectral form factor. And the reason why is because people understand better how these features of chaotic systems are represented in the behavior of the spectral form factor. So in a chaotic system, you have this energy level repulsion and spectral rigidity. And people have studied these features and how they are encoded in the spectral form factor. So essentially,
the spectral, this is the Fourier transform of the probability of having an energy difference, no?
It's a density correlation. Spectral form factor.
Essentially.
The density of eigenvalues.
Yeah, it's
Yes.
Z beta plus IT times Z beta minus IT.
Exactly. So the typical shape that the spectral form factor has in a chaotic system is it has some descent, falls to a minimum, which people call a dip. Then there is an increase called ramp, and then it saturates. And typically, initially, like the part of so energy level repulsion is what dominates at early times. And then as time increases, then you have these correlations between the different energy levels that kick in. And it is this spectral rigidity that people know that is responsible for the ramp here. So if you look at an integrable system, then you will not see this ramp. You will still see some shape like this, and then it will like roughly saturate to some number here. So this ramp, this ascent after the dip, is a reflection of the chaotic properties of the system. So one way to try to understand this peak is by comparing the time scale at which it appears and to what it corresponds in the spectral form factor. So if you carefully look at this, then you see that the peak appears before the plateau, which corresponds to the same time scale at which the complexity saturates. So then what you can say is that the physics that gives rise to the peak in spread complexity is the same that is responsible for the ramp in the spectral form factor, because by analysis of the time scales. So yeah, the physics that gives rise to the peak in spread complexity is the same physics that gives rise to the plateau, to the ramp in the spectral form factor. Yeah, it's very close to the transition between ramp and the plateau. And you have this quadratic, then linear, then saturation behavior. And if you look at the integrable case here, like I don't really, so by the way, this yellow line here is supposed to be like a time average, because here you only have like one realization of the Hamiltonian. So it's very noisy. So this yellow line is just some time average here in the spectral form factor. You have an oscillation, so that people remember, you have like an oscillation here in the spectral form factor. And this is responsible for these very nasty oscillations. So in fact, like the saturation is not really, the saturation value is not a good indicator of chaos or not in the system. So it's the peak that tells you if your system is in a chaotic phase or not. Yeah, so one question was like, is this peak structure only present for the thermal field double state? Are there other states for which you can see it? And this is what led us to look a bit more closely at random matrices. And in particular, we studied random matrix quenches. And I'm almost done. So if you can bear with me, maybe 5 or more minutes, it's okay. We have until 6. Okay. Okay, so one of the questions that I also had at the beginning was like, can you change this prefactor n to be something else? Can it be whatever function? And in principle, yes. So one type of modification that you might want to consider is this one. You might want to have, for example, n to some positive power of m appearing there. And this you can call some generalizations of spread complexity. And this can also be seen as arising from expectation values of that generalized spreading operator. Now, why would you care about these things? one argument that can be done in favor of these things is that typically when you look at quenches, you have a system, a Hamiltonian in the pre-quench, and then you do a quench, and then you have a system after the quench, the post-quench. And you want to say, for example, something about the probability of measuring an operator, of an operator having a particular value before and after the quench. So it turns out that if you look at the spreading operator, there's also like some probability distributions of measuring this operator before and after the quench. And what these authors and collaborators showed is that these generalized complexity notions appear in this kind of questions, in this kind of problems, natural to quantum quenches. These are also related to, these are also complexity measures in the sense that I mentioned at the beginning. The Krylov basis provides a minimum for these cost functions. So these are like higher order quantities that also measure complexity. Now, one very naive reason why you would be interested in them, if you wanted to look more closely at features like the peak, is that here the red plot is the usual spread complexity, and this like brown golden plot is like C2 by taking m equals 2. Qualitatively, it looks like the peak is more present here. I will be more precise later. But qualitatively, the peak is more visible if you take these generalized complexities. So that's one reason why you would like to look at them. And then this can help us see better if we can see the peak for other states other than just the term of the double state.
So wait again. So here we just took a single matrix. Did you say? Or?
Yeah, in this example is just for one realization of a GOE matrix. Yes, that's true.
Yeah, but you should do the average. You know, you should take.
Of course. Yeah, of course.
Well, the entries are randomly chosen, right?
Yes. Yeah. Okay. Yes. I see.
Yeah.
So it would be a generic matrix. Yeah, for sure.
Yeah,
but
exactly.
it's generic enough.
Exactly. Yeah.
Of course, like as you say, like the power of.
Yeah, but this is sorry, I got it different. But,
yeah, the power is of this kind of like matrices is that you can take different realizations and then you can do computations and then you can do some averaging over these quantities.
This matrix you take to be the H. You compute the powers of this matrix acting on a fixed vector.
Yeah, exactly. This is what you do. So this is just an example for one realization of this kind of matrix for that size. This is just like a small motivation for why we would like to study these things. And now the type of quench protocol that we were looking at, which is a quantum random matrix quench, is the following. The protocol is implemented by that kind of random matrix. It's a big matrix where A, B, and C are also matrices. And you can think that this is some Hamiltonian, like you start from some system that has a Z2 symmetry, and the off diagonal terms are breaking this Z2 symmetry of your system. So here, these diagonal matrices, A and C, are some symmetric matrices that you can sample from a normalized random matrix ensemble with some fixed measure. You can choose here, beta is this Dyson index, and then you can choose it to be like, for example, GOE or GOE. And then you sample your matrices A and C from this ensemble. And in the GOE case, then you take this, the entries of the Bij of the B matrix to be numbers drawn from a normal Gaussian normal distribution with zero mean and fixed variance. And in the GUE case, then these Bij's are complex numbers where each individual, the real part and imaginary part, are independently drawn from a normal distribution with zero mean and fixed variance. So
I just need some more intuition about this. What does the PDF of the gap of this guy look like?
I'm sorry?
What is the probability density function of the gap, of the spectral gap of this guy look like? Does it still follow the Nernst-Normalize or?
Yeah, so for example, if you, the point is that, so for, okay, let me be more precise. For H plus minus 1,
yeah,
this big matrix will also correspond to the same universality class as this individual matrices for H plus minus 1.
Yeah.
For H different than plus minus 1,
yeah,
it will not correspond to either of these universality classes.
Right, okay, then it's, okay. And which one do you consider? Like, what value of H do you consider?
So this is where the
right. Okay, yeah. Okay, that's where the quench comes in.
This is where the quench comes.
I see.
Exactly. So for the before the quench, the pre-quench Hamiltonian is this one where you choose H equals to be -1. And then in this case, this big matrix also corresponds to a fixed Gaussian ensemble after you choose if you want to consider like orthogonal or unitary. And then after the quench, you take H plus equals to 1. And also this big matrix will also correspond to the same universality class. And the reason why we want to study quenches is because this gives you more states at your disposal that you want to study. And this is one of the reasons why we were interested in this.
But you only go from in the quench trajectory, for lack of a better term, like you only go from this between the same universality classes. Right?
Yes, exactly. We don't.
Okay. We don't jump to different. Okay.
No. One important point in this type of quench protocols is the fact that the pre-quench and post-quench Hamiltonians are independent from each other. And in this case, independence means that their eigenvalues are completely random with respect to each other. And this is something that you can verify by computing what people call the inverse participation ratio. So here are just like plots of this so-called inverse participation ratio. And the blue dots, there's like a typo there. The blue dots are supposed to correspond to the IPR of a fixed post-quench eigenstate computed with respect to all the pre-quench energy eigenstates. The fact that there is no energy dependence means that these two Hamiltonians are independent with respect to each other. Okay, so this is just some preliminary results. Like this is a paper that should come hopefully before the end of the year. So a simple question is like, we want to study this spread complexity and we want to study the peak better numerically. So here I just want to show, for example, how the peak behaves for different states, for different generalized spread complexities. And the point is that this is for the Gaussian orthogonal ensemble corresponding to beta equals 1. This is a small average only over 4 realizations. Of course, the point of doing this average just like smoothens the curve. That's just the point of taking the average. And this is for a very modest size of just 1,000 by 1,000 matrix. And the point is that here you can see, wow, this is really slow, but it's so cool. You can see the red curve corresponds to the post-quench TFD state, which we use as a benchmark for the behavior. We contrast the behavior of other states with respect to this post-quench TFD state. So what you can see is that even for these other states, for example, you can still see a peak before the saturation. I will be more precise later, but qualitatively you can see it. And this is even more evident if you consider, for example, GUE. In GUE, this peak is a lot more clear even for states that are not the thermophile double state. So I will not bother you with the details of this very, very ugly slide. But the fact is that you can also quantitatively study the peak. And there are several things that you can say about the peak for different states and for different generalized complexities. So let me end the talk. I guess, I don't know if a summary is needed or not, but let me just quickly go through it. What I mentioned at the beginning was that chaotic quantum invariant systems have these Lanczos sequences with asymptotic linear growth. The converse is not true. Linear growth does not imply quantum chaos. And this linear growth in QFTs is expected from the poles of the two-point function. IR scales, introducing IR scales in your theory induces a staggering in the Lanczos sequence. However, there's still this chaos bound, which is still true. Putting cutoffs, essentially UV cutoffs, essentially amounts to regular UV regularizing your theory. So then you recover behavior that you expect for integrable case for a free QFT. Perturbative interactions do not change the behavior much. You just get like a decrease in the growth rate, but it's still linear growth of the coefficients. For the billiards, it seems like these Lanczos coefficients, satisfy this chaos bound and saturate at small temperatures. And there are some papers, I think you were also in, no, you didn't participate in this paper. You are?
Yeah.
Same, yeah.
Yeah. So you also looked at triangular billiards, right?
Yeah.
You didn't put commas between all the names, right?
Sorry?
There's a comma missing.
Yeah. So for state complexity, the fact that the peak occurs before, but very close to the plateau, leads us to think that it arises from spectral rigidity. The early time is universally quadratic, and it's independent of the properties of the Hamiltonian. And the saturation value and timescale of this spread complexity is not a good indicator of quantum chaos, also because it depends heavily on the initial state. There's some ways in which people have tried to go around this, and there are some papers that tackle this. And I will skip this part, and then let me just end with some open questions on future directions. So for people who are interested in holography, one reason why you would want to be interested in this spread complexity and Krylov complexity is the fact that recently there has been works which have matched the wormhole length in JT gravity with the spread complexity of chord states in a very special limit, scaling limit of double scaled SYK. And very recently, I think last week or 2 weeks ago, there was another paper which was able to find the saturation value of spread complexity in the same context. One question is, for example, do other holographic complexity proposals correspond to different generalizations of spread complexity? One thing that might be more familiar to you is the so-called switchback effect, which is a property that computational complexity has. Computational complexity behaves in a very particular way. There's some time delay whenever you have an operator inserted in your circuit that propagates. The time at which you insert this perturbation in your circuit gives you a time delay. And this is something that people are also interested in looking at in holography, and it's a defining feature for holographic complexity. So one question is, do spread and Krylov complexity, are these sensitive to this phenomenon? I think that probably I don't know if with tensor networks, you can also see a switchback effect, but it's something, or realizations of these things in quantum circuits may be interesting also to look at. There are some interesting works that say that Krylov is not a measure of distance between operators, and spread complexity is not a distance between states, simply because they fail to satisfy the triangle inequality in time. But at the same time, there is a relation between the time average of spread complexity and an upper bound on Nielsen complexity. So people found a mathematical statement relating these two quantities. So one question is, what is the precise connection between spread complexity and other measures of state complexity? And finally, and in relation with quantum chaos, it would be interesting to tackle precisely these things such as many-body localization. And there are statements like scrambling is necessary but not sufficient for chaos. So I think perhaps it would be interesting to look at this at quantum chaos and thermalization from this perspective, and maybe there are some interesting things to look at. And I think that's it. Thank you very much.
I have a question regarding the last point of your outlook. Yeah, it will be short. I'm also interested in this, in the dependence on the initial state, because, let me play a bit of the demon's advocate. You or people you studying this Krylov complexity usually say that, these coefficients A and B, they have information not only about the Hamiltonian, but also about the initial state, like if it was a good thing. That might be, but you can also say that that's a bad thing, because you want, at the end of the day, to extract some property like chaos or not chaos that is about just the Hamiltonian, not about the state. So in that sense, it's a bad thing that you have that information there. And for sure, if you choose as an initial state an eigenstate, you won't see anything.
Of course, yeah.
And I guess that by continuity, if you choose an initial state that is close to an eigenstate, you also don't see much.
Of course.
It's called you choose a random state, and for sure it will never be an eigenstate, so you are fine.
Yeah.
So can you say something about this? So is this really like that. You just choose a random state and hope that it's not an eigenstate, because for sure it will never be an eigenstate, so you will be fine. Or it is really a problem, and since I saw there that you wrote, or yeah, what about the initial state dependence?
Well, I think.
Or this is in another context, maybe.
No, it's in this context, and precisely like what you're saying is, I think the reason why it's important to understand these questions better. So I think you might want to understand for which states you have like universal features, and maybe there are different properties, like maybe what about the entanglement of this state? Are there any property? Can you classify spread complexity with respect to some other properties of different states? Like, I think this is more than a complaint. This is like an opportunity to do many things. And I think that this is like something that is not at all being explored in the community, at least in high energy. People like me usually just consider thermophile double state, because there you have very concrete ideas in holography of what this state means. But if you take like any other state, like we don't really have a good handle of like what is a holographic picture. But from the quantum information perspective, I think, and more from like the many body condensed matter community, these are questions that are definitely very important. So I agree with.
Do you know about quantum scars related to this NBL point?
Yeah, I think some people have tried to study quantum scars in this context, but I have not seen many papers. I don't know if you remember other papers, about quantum scars.
I tried to do it in
quantum scars.
I tried to do it in the computer before, but yeah, I mean because the statistics, I mean, depends on, so it depends on how you introduce scar in the Krylov approach. Okay, for example, you can consider some triangle, some billiard. You can find scar state. Okay, find some scar state, but if you only sum over those scar state, then it just relate to how their spectrum, what's the spectrum statistic of those scar state. So then I mean, yeah, then you will have another behavior complexity. Yeah, but just so yeah.
I just wanted to I mean, like I can certainly write down a Hamiltonian for you, which will have quantum scars.
Yeah.
Like PXP model.
Yeah.
I think even in these billiards, for example, you also have scar states.
Yeah.
But I think that at least we didn't look at them, but I don't know if other people looked at these scar states. But these are important because they are close to what you would think of like classical states in some sense, right? So this is obviously like an important question, I think, also for practical realizations of these ideas. Okay.
I want to think of Krylov complexity as as related to some state complexity like Nielsen or quantum circuit complexity. How worried should I be that the Krylov complexity seems to depend so strongly on the Hamiltonian?
Well, you're focusing on the time evolution in this sense, right? I think probably what also would be interesting is to try to generalize these notions to other kinds of unitary circuits, not just unitaries that arise from your time evolution, right?
Yeah, I guess you can put it that way. I guess the question was, like, if you want to imagine you want to show that Krylov complexity somehow, let's say in some regime, some short time regime or some early evolution regime of some unitary evolution, maybe you can show that the Krylov complexity is equal or is within some bounds related to the Nielsen complexity.
Sure.
What sounds to be an obstacle to this is that the Krylov complexity is always defined with respect to Hamiltonian.
Yes.
Specific Hamiltonian. And I imagine that if I take a different Hamiltonian, this could change completely.
Of course. Yeah.
So, but that's not the case for Nielsen complexity. Nielsen complexity is just defined as and two-body Hamiltonian.
Sure.
Like you fix, of course, your threshold on how on the weight of your terms that you allow in your metrics, right? But so that seems to be a fundamental difference in how these quantities are defined.
Yeah, I agree.
Is it a fundamental difference, or is it like the Krylov complexity kind of secretly doesn't really matter which Hamiltonian you pick, and you're going to get similar behavior?
Otherwise, you wouldn't have a difference between the
well, I guess like forgetting for a second that you were interested in looking at quantum chaos, like if you were just thinking about I just have a Hamiltonian and I just do time evolution. I think that, yeah, you're right. Like in some sense, these are different kinds of questions. So I don't know if you generalize these to
How
other.
is defined this Nielsen complexity?
Think of it as, what I'm gonna say is not exactly true, but think of it this way.
Okay.
Think of it as the minimum time required, if you're allowed to apply a time-dependent two-body Hamiltonian of some fixed norm, let's say, at each point in time. I'm allowed to apply a two-body Hamiltonian with, two-body local terms or k-body local terms for a certain amount of time, and what's the minimum total time I need to reach my states?
And the minimum is over.
Overall possible schedules of Hamiltonians.
Well, but here you can also minimize over different Hamiltonians, and then you have a Hamiltonian independent quantity.
It is, the Nielsen complexity is.
You can do the same thing
Yeah, yeah.
starting from the Krylov complexity. And
You want to minimize overall possible Hamiltonians?
why not?
Yeah. So you find it more equal?
That's it generally does for
Yeah.
the Krylov for the Nielsen complexity. So
Well, the definition is very different, like, the Nielsen complexity, like the idea of the Nielsen complexity is actually, like, you can see it as a Riemannian geometry on space of all unitaries or states, right? So like, it has a structure, you can think of these X, you can write these equations.
But this,
like that.
the Nielsen complexity is the Nielsen of a state. So I give you a state vector, no?
Right, I
And
mean,
then
it's
is
defined for
the-
unitaries, but you can also define it for states, if I remember correctly.
But I mean,
You'll know.
like two states in some sense, right? Like how far they are, what way from each other, right?
Well, you need a reference, sorry, if you have one, you need to pick a reference, like the identity matrix, or unitaries, or the zero state.
And it's like, how do I reach this with these allowed operations? And I think that,
Does it upper bounding circuit complexity or lower bounding?
Anyone can
Yeah.
know how you.
for sure you can always
So,
minimize,
so
but
you
I
can
think
grab
matrix
some
different.
Yeah, actually.
Okay.
We need to know. So Nielsen geometry is also not really circuit geometry, right?
That's also true, yeah, it seems.
Well, I mean, but that's what you just mentioned. Like, it's like, or what your point just touched on. It kind of upper bounds and lower bounds the circuit complexity up to, like, how you choose your gate set, how your local two-body evolutions can simulate gates and that gate set, what's your accuracy, bunch of, like, some details, but like, morally, they're the same in different models. You can think.
Yeah, I think I don't have a good answer to your question, but we can chat more. Thanks.
did anybody ever dare to address the same question for time-dependent Hamiltonians?
Yes, it's extremely tricky. Essentially, you can think of like the simplest time-dependent Hamiltonian, like some you have a Hamiltonian, essentially like similar to the quench that I presented to you, that you have two time-independent Hamiltonians, and then you have some transition at some t equals 0, for example. And even there, it's extremely tricky to do these things. So it's like time-dependent Hamiltonians is a very, very big challenge here. And people don't know.
Yeah, all these lands of things, it doesn't apply anymore because you don't just, the exponential is not just the power series, right?
Exactly.
You have the time order, the integral of the exponential.
Yeah, no, it's a horrible thing because then you want this power series, then you have to take derivatives of the Hamiltonian, or depends on how time dependent enters your Hamiltonian, right? But it just, you cannot apply the same formalism, I would say.
But you could do it in like at every instantaneous point, just update the new Hamiltonian.
Probably, but it's also extremely
And then
messy.
try to
Yeah.
find a relationship to the actual question.
Yeah, no, I think this is something that one of my collaborators tried, and it's a big mess. It's a big mess.
I mean, very, very stupid and simple thing you could do is like basically expand as a Magnus expansion and get a time independent Hamiltonian up until some time period.
Sure.
And each of your Kirillov is the
Exactly.
Magnus. Yeah.
Exactly, yeah.
Yeah, you can do.
It was the zeroth order simplest thing. So this ties into things like pre-thermalization, for example, where
okay.
people ask like, for time-dependent Hamiltonians, like, well, how do I determine the times, like, if I wanted to determine a time scale up until which my effective Hamiltonian is a good description of the dynamics, how do I do that?
Mhm.
And basically what people do is they compute the Magnus expansion up until some time period.
Okay,
And the idea is that, okay, up until that time period, this effective time independent Hamiltonian will capture those dynamics.
I see. I didn't know, but
Yeah.
Just to program that in the computer would be
It's a big pain in the ass. Yeah.
Yeah.
Another related concept to the Magnus expansion in quantum optics, for example, is something called the rotating wave approximation, which is basically a zeroth order Magnus expansion.
I see.
Yeah.
Maybe you can tell me more.
Yeah, sure.
The chaos bound for OTOCs is based on the energy properties of the right?
Yeah.
Is like this Krylov bounds the chaos energy. Is this also argued based on some energy properties, or what is kind of the reason behind it?
Behind this one here.
Yeah.
So in the original paper, I think they essentially tried to extrapolate this infinite temperature bound, but they didn't give like, essentially they tried to argue something along the lines of the poles of the 2-point function, but I think they were able to show a less tight bound where you change this 2A to 4A, but then it's not clear if this part is also satisfied. But this is like I don't know. I don't know if there's like some progress on this bound.
I don't know. It's still, we may be a conjecture.
Yeah, we don't know.
But like this, maybe on a related point, like this is so what's the mechanism for deriving this new chaos bound from the Krylov? Like what's the logic?
At infinite temperature, this was just based on some properties of these Q complexities, these operator growth measures. This is something that they showed at the mathematical level for that class of operator growth measures. I mean, it's slightly technical, but I think in that paper you can see it. But this one is just a conjecture. They didn't provide any.
Right.
Thank you. Sure.
I don't know if you know this work by Svidnicki on generalized ETH. So what they do is they basically rederive this chaos bound for a system of ETH, which is ETH-like. Which we basically just take the usual ETH condition, where we like take the expectation value, the 1-point function of them observable in the energy eigenbasis. So you're going to have a diagonal component and an off-diagonal component. But the point is that if your off-diagonal component has non-Gaussian entries, then this basically allows you to bound the optimum exponent and then rederive this bound.
Yeah, I'm not familiar with this derivation actually.
Yeah, it's I personally like it because the original Maldaceno one seems to come out of heaven.
Then you have like an argument for what your C behavior and harmonies that satisfy
ETH. Yeah. Well, yeah, that's why I said ETH. It's ETH restricted.
Yeah, I think as far as I remember, like I have not seen people tackle this bound using ETH. What I have seen people do is understand better bounds on the Krylov space dimension by using ETH. So for operators, you can use ETH essentially to try to provide some bounds to the dimension of Krylov space for operators.
Because that would be very interesting to relate this non-Gaussian ETH to some quantity.
Yeah, I agree.
Actually, people try to apply ETH to study the plateau of the length of the coefficient. The plateau is no. It's
the saturation.
Yeah, the saturation value, right?
Saturation after that, it goes.
Yeah. So this was like in the thermodynamic limit, right? But if you take like a finite dimensional Hilbert space, then this is also just like the coefficients, but typically these coefficients will grow, saturate, and then go back down. And Krylov complexity will grow and then it will saturate. And this
should also have some recurrence down, because you have some recurrence time in finite dimensional system.
I don't know if people. I don't know.
No, that is based, in the totally integrable triangle, you will see that.
Sure. If you have like an integrable system, then you have recurrences at finite time.
If you have a finite dimensional system, then you will have recurrence time manifestly. Like at some point, you have to return back to your initial state, right? So your complexity has to drop down.
But I don't remember seeing anybody like go up until the recurrence. This is infinite dimension.
Yeah, this is
infinite dimension, but indeed,
okay.
Just consider a triangle, an integrable triangle, then you will see the drop down.
Yeah, this is in the infinite dimensional limit. This growth is forever. Yeah, this is also the regime in which your OTOC grows exponentially, which is not true for all timescales also, right? I don't think I have more to say.
Or maybe we can try.
You
Yeah, sure.
elaborate. Yeah, thanks.
Sure.